Here's a multiple choice question. What's the integral of sine x over x from 0 to infinity? Richard Feynman would define a function f of y to be this integral with sine x replaced with sine yx. df over dy would be the first derivative of this integral, or the integral of this derivative. X is independent of y, so we place this x here. The first derivative of sine yx is cosine yx times x. X and x cancel. We have the integral of cosine yx. It's simply sine yx over y. We plug in the lower limit and upper limit. Well, over here we're stuck. So Richard Feynman would redefine another function f of y to be the integral of e to the power of negative yx times sine x over x. Now df over dy is the first derivative of this integral, or the integral of this first derivative. Sine x over x is independent of y. We take it out. We take the first derivative of e to the power of negative yx. It's an exponential function, so we have negative x times this exponential function based on the chain rule. X and x cancel. Now we have integral of the product of exponential function and a sine function. We can express the sine function to be a linear combination of two exponential functions. It's e to the power of ix minus e to the power of negative ix over 2I. And then we have two integrals here and here. They are the integrals of two very simple exponential functions. So how do we integrate exponential functions? Well, the integral of an exponential function is itself divided by this coefficient, negative y minus I here on the bottom. And then we have this expression plus this expression. Now we plug in the lower bound and upper bound from 0 to infinity. When you plug in infinity here, e to the power of negative infinity is 0, and also this disappears as well. So really we just need to plug in x equals 0. When x is 0, we have e to the power of 0, which is just 1. So we have this term left, and don't forget we have minus this term, and then we have I over 2 times y minus I. And this integral becomes this. We can combine this. We get negative 1 over y squared plus 1. This is trivial. This is just algebra. Now we know df is negative 1 over y squared plus 1 dy. We integrate both sides. And we get negative arc tangent y plus c. You can see this in any calculus textbook, but if you need the proof, it's here. How do we prove this? We can set y to be tangent t. Now we have this and this and this, because on the bottom you have 1 over cosine t squared, and 1 over cosine t squared is just cosine t squared. Now we need to evaluate the first derivative of tangent t. It's right here. You can just use the division rule in calculus, and then in the end you will see on top right here it's just 1 cosine t squared, and cosine t squared cancel. So we just have negative integral dt. It's minus t plus a constant. We now determine the value of the constant. Again, we have this function of y to be negative arctangent y plus c. We plug in y equals infinity, and we know the arctangent function of infinity is simply pi over 2. Now we have this c is equal to the f function of infinity plus pi over 2. When y is infinity, we have this integral over here, and it's pretty easy to evaluate. When y is infinity, this part becomes 0, so the result is simply pi over 2 for c. Now we have the expression for the function of f. It's negative arctangent y plus pi over 2. Finally, we plug in y equals 0. F of 0 is this integral, and this is f of 0. We plug in 0 here. What's the value of arctangent of 0? It's 0. This is 0. So f0 is pi over 2, and also f0 is equal to the original integral. Its value is pi over 2.